Thank you for the opportunity to present my work. Thank you for your patience. My name is Smigielska. I'm an architect based in Zurich, and I will talk about the development of my independent research of robotic rod bending applied to non-standard space frames, with the use of machine learning for material control. Being more specific, I'm talking about the springback of metal in the process of bending. So to guide you through the presentation, I will start with rod bending development. Then I will go through curve deconstruction and springback analysis. I will go through two projects which were developed recently, and I will end the presentation with a summary. So looking at the development of cold bending technology, one might notice that it didn't develop much until the 90s. It mostly used manual table benders. From the 90s, we had a big improvement of computer integration in the process, which shifted the technology from labor-intensive and hazardous process to safer, faster, and almost fully automated. Yet, it still did not integrate the material behavior, so those systems could not intelligently adapt to the conditions and the springback of the material. And springback, as in itself, exists in all metal forming processes, whether these are rods, whether these are tubes or metal sheets, due to its properties, compression and tension forces applied to the material. While being bent, and this process basically couldn't be automatically controlled until the year 2000. So in the early 2000s, industry started to use machine learning in order to predict the springback compensation to achieve the desired bending angles. Current machines, which are freeform benders, as you can see on the slide, can do that, but access to such machines is obviously reserved only for heavy industries. There are some precedents of employing the robots to the rod bending processes, like the one done by Supermaneuver, presented here on the photo, where the robot is used to hold and slide the rod while the bending operation is done by the external engine. In the other solutions, the springback problem was solved by overbending the rod and then bending it back to the desired angle value. But in general, to summarize the situation, this is the industry that possesses the knowledge of the material and the production, keeping it beyond architects' reach, which creates obviously the gap between the design and making. So this brings me to the question, can architect, having access not only to the digital fabrication tools, which we already have, but also to the machine learning tools, can we overcome those industrial limitations, not only for simple prototyping processes, but also for complex production processes? So, as an answer to those questions, I did my first trials with manual benders, with the idea that what I learned can be automated with the use of a robotic arm. I tried with different materials. Metal materials, I tried with different joinery systems, including structural glues, welding, resin, customized 3D printed elements, and elements of hard plastic that were milled. I have learned that the standard setup provides static rotary station and an external gripper to keep the rod in the position. But my idea was to actually simplify that process with the use of robotic arm, which serves both as a gripper and a bender. So what I literally did is I removed the bending element and attached it to the robotic arm. To follow that concept, two things needed to be developed. First of all, that needed to be the software, so instructions for the robot to grip, rotate, and bend metal rods, and the hardware, which is the tool head, again, that serves as a gripper and a bender. Separately, I needed a station to hold the rod. So the tool head is designed in a way that the bending happens between two bolts, as you can see on those schemes and photographs. They block and bend the rod just by rotation of the robot's 6 axes. I have gone through several iterations of those tools, ending up with the one that allows for a certain customization of bending radii, as presented over here. The holding station over here, the biggest black element, is designed to have different insets that can hold rods of different size as well. But as a next step, there was a software that allows for precise curve deconstruction to be read by the robot. So there are three crucial data types that we need for the robot to rebuild precisely our desired polyline curve. First of all, we need distances between consecutive bands. We need also angles between consecutive sections of the polylines. And we also need the orientation of the bands, meaning band can be positive, which means that we bend clockwise, or negative, which is counterclockwise, looking from the top. It is important to mention that that we need angles and orientations given twice for three-dimensional bands. As illustrated on the bottom on the right-hand side. We first declare the data for the rotation around the axis of the road, mentioned as X, and then around the Z-axis of the tool head. Two-dimensional band can be also declared the same way, very easily, just by declaring 0 degree for the first operation. Next step was to look at the problem of material behavior, springback. And this is where we talk about machine learning. In order to achieve precise bands of non-repetitive angles, I needed to obviously be able to predict the springback in a continuous way. It was necessary to build the continuous value predictive model of the material behavior, which is a functional relationship between two quantities mentioned on that scheme. It is desired angle X and the resulting band angle Y. Subtraction of those two result as a springback value. So to create this predictive model, I needed to collect, to create an exhausting data set by making physical tests. The bending test varied between 5 degrees and 180 degrees. The measures were done with mainly two methods. That was manual readout, the left-hand side, and the average readouts taken from the photos. So if we look at the charts representing bending angles and its corresponding springback values for those two methods, we can notice that the first method, manual readouts, is very imprecise. That data is dispersed, especially for low and high angles. It's hard to extract any continuous values out of that. While the average readout seems to be more consistent, and these were taken into account. This is particularly visible if we look at this chart where the values are mapped one on the other. After data acquisition, I came to data modeling. I used the polynomial regression as a simple machine learning method. Polynomial regression tries to fit the discontinuous data into continuous polynomial, trying with different degrees of curves, which you can also have a look at here. We can compare different degrees of those two polynomials represented by numbers from 1 to 6 on data sets from manual readouts, black color, and averaged readouts, which is green. It becomes obvious at some point that such a small data set consisting of only 120 points, which was the size of my data set, for such a small data set, it was obvious that the precision is a must. So there was no discussion which method I should use. Because for the project I wanted to do the imprecision of several degrees was absolutely unacceptable. Alternatively, there is also another method to fit the data, which is called bugging of random polynomial regression, which is particularly useful for small input data sets. Bugging of polynomial regression randomly selects several sets of training data points, then generates several polynomials. So these are those almost transparent lines, and then try to average that. The final decision of the choice was polynomial regression curve of this third degree. As a result of those developments, I was capable to precisely bend any angle I wanted with the precision of plus minus 1 degree. Having done that, I could say that this industrialized and encapsulated process was somehow taken out of the cage with those few solutions that I have mentioned before, meaning the hardware, very simple robotic toolhead, a piece of software with simple procedures of based on translation and rotation, and some data manipulations with machine learning, very, very basic machine learning algorithms. With such equipment, I was ready to have a look at some projects done within the technology. What? Yes, here. So, front desk. Front desk was a commission for AAN+1 gallery in Paris. Please feel free to visit. This is visit this piece and also a beautiful exhibition which is happening there right now, a solo exhibition of Artur Mamumani. The project was designed and built by me with Pierre Kutelik from the Computational Monkeys. It is an ambitious project because of its size. It's 5.5 meters long and it's also having the cantilevering form. Besides of the fact that the robotic rod bending technology was applied over here, we also tried to utilize some data-informed design strategies where input geometry is modified or validated by structural analysis and material constraints. So to keep that short, I will just say that the initial design started with two parametric curves, which created certain polysurfaces that were analyzed first with voxel-based structural analysis. Then we have developed then we applied wire grids to analyze them with finite element structural analysis. And then we fed the model with the material constraints to provide us with the final form that we finally produced. This is the representation of the voxel-based structural analysis. So you can see those two initial curves at the very beginning. We have optimized it with the use of a generic solver, Simplook Galapagos. As a next step, those wire grids were implemented to create a space frame that could also go through another analysis. Another generic solver would help us, would prompt us on right spacing for the grid. So you might notice from the top plan that the grid is varying according to where the stresses are the highest. We've done some mock-ups and tests. After several analyses, a final structural pattern started to appear. So the general shape was partitioned into 110 segments, and each of those segments were having following elements, as mentioned over here. Those chunks provided stiffness, and as such defines the sequential preassemble and welding, which you could maybe quickly see at this animation. So these are the principal bars, diagonals, top zigzag, and then another chunk. In that way, we have built the front desk of the length 5.5 meters. I will skip that. So yes, after the design phase, we pursued to fabrication. Bending took roughly 2 weeks' time, which was nothing compared to the time we spent on pre-assemble. That was 1 week, and also welding, which was another 4 weeks. Here you can see some close-ups of the final chunks located on the side, and the final views of the piece. This is how we look. And if we look at certain key numbers that are coming with this project, so in total it's 800 pieces, it's 340 meters of rods, almost 3,000 bends, out of which 2,400 angles are unique. As mentioned before, the assembly in that case was the most time-consuming part. 1 week of pre-assemble and another 4 weeks of welding. We needed to make more than 3,000 point welds, which at some point became almost like a hobby and a daily ritual. So this painful lesson led me to the next project in which I wanted to check another joinery methods. Which occurred to be hard PVC, tightly fitting to the 4 millimeters rods that we have used with Mateusz Wierzycki, who will be presenting here this afternoon. We did this column. It's currently being exhibited during Tallinn Architecture Biennale. It's 2.2 meters high. It's having repetitive elements based on hexagonal rotational symmetry. So over here we have 10 unique rods of the length of the 3 meters length, which is the size of the rods provided by the manufacturer. We then divide those curves, those rods into 3 or 4 shorter parts of the maximum length of 140 centimeters and maximum 14 bends on each element. The whole process, the whole process of bending took 1 week for only 1 person. And only 3 days to assemble by 2 people. However complex the assembly was, the time taken was significantly reduced comparing to the welding process. And as a summary, let's have a look at some key comparison numbers for those 2 projects. So, so for the column, the elements themselves were more complex because all the bends that we have used were 3-dimensional, while for the front desk that was only 40% of 3-dimensional bends. That's why it also allowed for sequential assembly. But for the column, we used all the bends were 3-dimensional, as well as we increased the number of bends at each element twice. So some of the pieces ended up having 14 bends in one go, which very happily, surprisingly, but also very happily, did not increase significantly any accumulative error, which proves the certain geometric precision of this technology. Because we used 3-dimensional bends, the assembly of the parts were more complicated, but we actually traded it with the repetitive elements and repetitive assembly pattern. Following those key numbers, I wish to also underline one keyword characterizing this independent research, which is simplicity. Simply because it's important to mention that this research and those projects were pursued with 1 robot, 1 operating person, with no additional numerically controlled equipment, no financial grants or scholarships, with only 2 people assembling the pieces, with no academic or institutional support, and with open source software. So I dare to say that this research represents a bit of a shift from industrial setup. On one hand, we have simple mechanics and versatile process. On the other hand, we have a simple application of machine learning that allows us to encapsulate knowledge, which so far was only available for specialists. So with machine learning, it was possible to preserve certain geometric sophistication without those specialists, without industrial or academic partners. But those very few partners that I have collaborated with, I wish to mention them now, and I wish to thank them a lot. First of all, it's ARIA Institute in Paris, which is a technological accelerator, which allowed me to use the robotic facility in Paris-Cergy, ABB Robotics. I would also like to thank Pierre Kutelik, with whom we have worked on the design of the front desk project, and Mateusz Wierzycki, with whom we collaborated on the column project. Lastly, I would like to thank Digital Knowledge Department at Paris Malaquais School of Architecture, where I led the intensive workshop of robotic rod bending this year in February with students where this workshop contributed a lot to the development and verification of those processes. I think it's also important to mention how where I see the potential of improvements and developments, which one can read over here. It's mostly about material elongation. It's about automation of precise readouts of the spring-back data. I'm very interested in employing multidimensional machine learning analysis by increasing the number of input training data and maybe clustering multiple robotic processes into one continuous workflow, like gripping, bending, cutting, with the emphasis on assembly, which occurs to be the most time-consuming for this specific applications. Thank you.